Hello student, how are you? I am Arunsir. Welcome to my channel Tuition Expert. Today in this class, I'll teach you Thermodynamics part 1. Student, in 2 class, I will finish the whole Thermodynamics class with derivations. And this will be very helpful for your school exam, NEET exam, JEE Main and IIT. You don't require to see the another video. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the IITJ exam and NEET exam confidently with a good rank. Now let's start about the class. So thermodynamics part 1. What is the meaning of thermodynamics? Thermo means heat, dynamics means motion. So this is the part of how heat produces the motion, the law, the process, the derivations, etc. related to heat and motion is the branch of thermodynamics. Thermodynamics. Important is first term is variables, state, system, and surroundings. So these terms are important. What is variables? Which factor, that is which factor varies, the values of which factor varies. Suppose pressure, volume, temperature, internal energy, etc. is variable. State means this is a cylinder and some gas is enclosed within the cylinder. Okay, this is cylinder and this is piston and some gas is enclosed within the cylinder piston. Now if we compress the piston, the pressure, volume and temperature of the gas changes. So at different position, suppose here state this is the position 1, here the values of pressure, volume, temperature is 1 in state 1, and suppose when the piston comes here, pressure, volume and temperature of the gas is another value. So this is the state 1, this is the state 2. Suppose at the piston is at here pressure, volume, temperature has another value. So this is the state 3. So state means a condition or a position at where pressure, volume, temperature, that is variables, has attained a particular value. System means this is a system, cylinder and piston makes a system. So this is a system, this is closed system because a gas is enclosed by piston. This is closed system. And surroundings means the air, that is all the particulars except this system is called surroundings. That is here air. So we can say that system plus surroundings, make the universe. Thermodynamic variables property, two property, extensive and intensive. Extensive property, or this is an example, an intensive property, the variables which does not depend on the mass. Example temperature. System 3 system, open system, closed and isolated. What is open system? Here mass and heat both transfer or exchanged. We can exchanged. Suppose example, we boil some water in a container. Suppose this is iron container or aluminum container. We boil the water. So when we boil, the water vapors goes out to the surroundings. So and also heat. Boil in closed system, only heat is transferred, heat is exchanged. In closed system only heat is exchanged, not only heat is exchanged. Here heat, mass and heat both transfer. here only heat is exchanged, not mass of gas. In a pressure cooker we boil some water. And what is isolated system? Isolated system, here both mass and heat both are not exchanged, does not exchanged. Heat and mass both does not exchanged. Example of, suppose this is ice cream box container, no heat is goes from inside to outside, or no heat is entered from outside to inside, and also mass remain constant. That is, ice cream box is the example of isolated system. A heat and mass both does not exchange. Work done on a gas equal to pressure into change in volume, P into del B. Work done on a gas by constant pressure equal to pressure into change in volume. This is very important things we apply throughout the thermodynamics law. We use this theory, W equal to P into del B. So how comes work done equal to pressure into del B? Suppose this is some gas is enclosed by cylinder piston. Now the piston compress the piston. Now the piston comes from this position to this position. Suppose this volume is V1, this volume is V1, and this volume is V2. And when we compress, the pressure remain constant. Suppose pressure remain constant, we take the pressure remain constant, but pressure may be changed. Suppose first we consider the pressure remain constant. So at constant pressure, what is the work done? Work done equal to, we know, force into displacement. Suppose this is x, displacement of the piston is x. So force, what is force? Force should be applied if the pressure of the gas is P. Suppose P and area of the piston is A. Now force required to compress the gas. Force equal to pressure into area. If pressure of the gas is P, then P into A is force into displacement. What is A into X? Area into X. This area into X equal to this volume. What is this volume? This volume is P into del V. That is P into V2 minus V1. P into V2 minus V1. Okay. So work done equal to force into displacement, force equal to pressure into area, and A into X equal to del V, and del V equal to V2 minus V1. So work done equal to this diagram. What is indicator diagram? What is indicator diagram? Now we know, if we draw pressure versus volume graph. Now suppose a gas at constant pressure, the volume increases from V1 to V2. Suppose the volume of a gas increases from V1 to V2 at constant pressure. At this particular pressure, volume of the gas increases from V1 to V2. Now this area denotes what? This area equal to length into breadth. Length is this pressure particular P. This length is P, and this length is V2 minus V1. This length is V2 minus V1. So P into del V. Area of PV diagram equal to this. Now pressure into del V equal to work done. So we prove that work done equal to area of the PV diagram. This is P versus V diagram, and a graph is present. Suppose pressure and volume of the gas is varies like this way. PV, this graph equal to actually PV equal to constant. Now what is the area? This area is, now this area represents the what? This area represents the work done by the gas. To find this area, we have to integrate this. Suppose this is dV, this is pressure. So dW equal to P into dV. Now work done equal to P dV. Suppose volume V1 to V2 increases, so V1 to V2. So this is the work done, and this is also the area of this figure. This diagram denotes the cyclic process. So what is the work done by the cyclic process? This is not zero. Work done by this cyclic process equal to area of this figure. Now what is the area? suppose this is pressure P2 and this is P1 and this volume is V1 and this volume is V2. So work done by the gas equal to area of circle, which is equal to pi into r square. Now here r square is r into r. Here diameter equal to what? Diameter equal to, we can say diameter equal to V2 minus V1. Also this is the diameter P2 minus P1. So this value and this value are same. Now diameter radius equal to V2 minus V1 by 2 equal to P2 minus P1 by 2. So we can say that pi into r into r, which is equal to pi V2 minus V1 into P1 minus P2 minus P1 by 4. So this may be the result. This is the result. Also it may be whole square. Also it can be written as whole square. Positive work done and negative work done. What is positive work done? Suppose enclosed within a cylinder piston. Now here heat is supplied to the gas. So heat is supplied to the gas, that is Q is supplied to the gas. Now due to now pressure increases, so the piston moves upward. So piston moves upward. This is the gas expands, and we call that this is the work done by the gas. So here gas expands. If the piston moves upward, then we can say that positive work done equal to work done by the gas. That is gas expands. When gas expands, volume increases. Volume of gas increases. We can say that this is the positive work done, or work done, that is work done by the gas, or gas expands or volume of the gas increases is the called positive work done. What is negative work done? Suppose this is a cylinder and this is a piston, and we when we compress the gas, that is compression of gas, that is work done on the gas. When we compress the gas, some external force applied on the gas, that is work done on the, it is called work done on the gas. It is called work done on the gas. Work done on the gas, that is compression of the gas. That is volume of gas decreases. This process is called negative work done. This process is called negative work done. So in negative work done means work done on the gas, that is volume of gas decreases, or compression. When compression of the gas take place or volume of the gas decreases, this is called negative work done. Now why thermodynamics part is so important? Because we create the motion in earth. What type of motion we watch? Every automobile engine, every vehicles, ship, aeroplane, every motion in sky, water and in land, every motion is created by the heat. Heat comes from petrol or diesel. That is in automobile vehicles, ship, airplane, etc. For every motion is run by the petrol or diesel, which produce the heat. So that's why thermodynamics law process is very important. A cylinder piston is present. Every automobile engine, a cylinder and piston is present. Now a petrol and diesel is combust in a chamber. So a high pressure gas is produced. Most type of petrol and diesel combustion in a separate chamber, and the high pressure gas produced in this chamber comes through a pipe and enters in the cylinder piston chamber. Here is a valve present, and also here is a valve present. Valve means which allow the gas in one direction. When gas comes in reverse direction, the valves closed. This is the function of the valves. Valve means a system which allows the gas to pass in one direction. When gas comes backward, then the system closed. This is called valves. Now a valve present here. So when gas is introduced in this cylinder piston chamber, this valve opens. opens. Now here high pressure gas pushes the piston. Now here this is here is a rod, two rod connected. This is called crank mechanism. Now crank mechanism. Now here and this rod is connected by rod, and this rod is joined in a axle of the wheel. So two wheels of the car is here. This is two wheels of the car is joined by axle, and this axle is connected by a rod. This rod is connected by crank mechanism. Now when the gas moves in this direction, then the rod pushes in this direction. So when this is push, it produces a motion, it produces a circular motion this way, because when we push a disc, suppose this is a disc, suppose this is a disc, when we push, suppose this is a disc, and the disc can rotate about this axis. Now if we apply the force along the tangent of the disc, then it moves, a torque is produced, so it rotates. Now up to this the piston moves upward, Now when it returns back, when it moves up to a certain limit, now this valve closed, and this valve opens, There some gas emits or emerge from the cylinder piston enclosure, from the cylinder. Here some gas emerge or emits from the cylinder. Now when it reaches up to certain, level, due to weight of the piston, it comes down. Now this piston, now this valve closed, and the piston moves down. So when it moves down, then again a force is applied in this direction. So here when it moves, force is applied along upward. When it comes down, force is applied downward. So due to this, a torque is produced, and this system rotates in a circle. When the axle rotates, then this also rotates. How petrol and diesel produces the motion of the car? The engine. I just show the simple process, simple diagram. There are some complex, but basic operation is this. So I explain how petrol and diesel produces the motion of the car. And this is the branch of automobile engineering. I just described the simple example how heat is produced in automobile engine. Thermodynamics. This is a thermodynamic system. Here heat is entered into the gas, and the piston moves upward. That is work done by the gas W, and also some heat is emerged, some heat is ejected from the system. In automobile engine, we see that some heated gas, sometimes with sparking, comes out from the car. So some heat is ejected from this system. Now now heat is supplied to the system, some heat is ejected from the system, and exchange a work is done by the piston, system. I have already discussed that how heat is produced, the motion of the car through a mechanism. Now this is a system. This system means what is it? So this is a system. What is system? System contains a container plus working substance. Here gas is working substance. So system means a container plus working substance to produce a system. Outside the system, whole the universe is system plus surroundings, we called universe. So container plus working substance is from the system. Now here some heat is produced. What is the first law of thermodynamics? If some amount of heat is supplied to the system, then system performs a work, and some heat also rejected from the system. Q amount of heat supplied to the system equal to change of internal energy. Now what is internal energy? just I will describe change of internal energy plus work done by the system. Q equal to del U plus W. This is called first law of thermodynamics. Q equal to what? Q equal to heat supply to the system. Net heat supply to the system. Del U. So I write here Q equal to heat, net heat, because some heat is rejected from the system. Net heat supplied to the system. Net heat supplied to the system. Q del U equal to change of internal energy, change of internal energy of the gas, and W equal to work done by the system. Work done by the system. Work done by the system. Now what is the internal energy? Internal energy is denoted by U. This equal to actually sum of all type of energy possessed by the gas molecules. That is, a gas has different type of motion due to its velocity, kinetic energy, and due to its particular position. Due to the particular position of the gas molecules, it possesses some potential energy. The gas molecule also vibrates, so vibrational energy plus due to the pressure energy. So sum of all type of energy is internal energy. We cannot measure the absolute internal energy of gas system. We cannot measure the absolute internal energy of a gas molecules, but change of internal energy can be measured. So here, so important point is we cannot measure the absolute value of internal energy, but it change. Del U means change of the internal energy. Change of internal energy can be measured. Change of the internal energy can be measured. So change can be measured, but we cannot, actual value cannot be measured. Del U. So here we write always del U, change of internal energy. Here we write del U, change of internal energy, change of the internal energy can be measured. So we here always del U, not U, not absolute value. This always here write we change of internal energy. This is the word done. So now describe this is the first law of thermodynamics. Now del U equal to change of internal energy equal to final internal energy minus initial internal energy. Final minus initial. Now what is Q? Q equal to heat supplied to the system and W equal to work done on the system. Supplied to the system, suppose this is Q1 and heat is rejected from the system. This is a case. Suppose this, we consider this case. Here heat is supplied to the system, some heat is rejected from the system. Upward, a friction acts on the piston, that is piston moves against the friction which acts between the wall container and the piston. So when the piston moves upward and friction acts to the piston, then we can say that work done on the system. So this is called, suppose W1, and this is work done on the system W2. Now here we can assign the sign. Q1 is positive because our aim of thermodynamic machine is to get some work done by the system. The aim of thermodynamic machine is to get some work done by the system. So our aim of machine, purpose of machine is to get some work done by the machine. by the machine. Machine is written as /c. This is symbol of machine, m/c. To get some work done by the machine is our purpose of machine. Always. So which factor helps the work done by the machine? Or take this is the positive factor. We take this is the positive factor. So Q1 is positive easily. So work done by the system is more easily. So this is positive. And as heat rejected from the system, when some heat, this heat is not used, so Q2 is negative. So Q2 is negative. Q2 is negative. So Q2 is negative, and work done by the system is W1, which is we required. This is our purpose. So this is positive, and work done on the system, that is friction. Friction opposes the motion. So work done by the friction is negative. Negative. That is which factor help the machine to work. Which factors help the machine to work? We take this factor is positive. These factors are positive, and which factor prevents to machine the work? We take these factors are negative. So Q1 is positive. Q1 means heat supplied to the system. This is positive. Q2 heat rejected from the system. Heat rejected from the system. Okay, which we take negative. And W1 work done by the system. Work done by the system. Work done by the system, which is positive. Work done by the system. W2 work done on the system. We take this sign is negative. Negative. So here heat supplied to the system positive, because this heat helps the machine to work. Heat rejected from the system. As more heat is rejected, then machine does not perform well. So this we take negative. Work done by the system. This is our purpose. So this is positive, and work done on the system, that is the friction. Here friction. This is we take this is negative. In chemistry, in thermodynamics present, chapter thermodynamics present, and physics, thermodynamics present difference of sign convention in physics and chemistry. In physics, our purpose is to get some work done by the machine, but in chemistry, our purpose is preference to put on the internal energy of the gas. In chemistry, sign convention, chemistry, the purpose is main aim how to increase the internal energy of gas. Internal energy of gas. In chemistry, main aim is how to increase the internal energy of gas. So which factor increases the internal energy of gas? We take that factor is positive, and which decreases the internal energy of the gas, that factor is negative. So in chemistry, our main aim is how to increase the internal energy of the gas. So suppose this is a gas, and internal energy is U1. Now if we supply some heat, then the internal energy of the gas increases U2. Suppose U1 and U2. U2 is final internal energy. Internal energy of the gas increases. So here heat supplied. So here Q1, that is Q is heat supplied. Heat supplied on the gas in chemistry. Heat supplied on the gas is positive, because heat supplied increases the internal energy of the gas. Now for pressure, if suppose this is a gas and we compress the gas through the piston, we compress the gas. So work done here, work done on the system, work done W2, which is work done on the system, this, if we compress the gas, the temperature, that is internal energy of the gas increases. Now internal energy, temperature of any gas express the internal energy of the gas, internal energy of the gas, temperature of any gas express the internal energy of the gas. So as more temperature of the gas means its internal energy is more. Work done on the, so when we compress the gas, then its pressure increases, the temperature also increases, that is internal energy increases. So here work done on the system can be taken as positive. Here work done W is positive because work done on the system increases the internal energy of the gas. Work done on the system, if we compress, that is the pressure increase. As pressure increase, the temperature increase. Pressure is proportional to temperature. As pressure increase, temperature increases. Temperature increase means internal energy increases. So work done on the system is can be taken as positive. And when the gas expands, when the gas expands, this is what done by the system. As gas expands, pressure decreases, temperature decreases, pressure decreases, temperature decreases, so internal energy decreases. That's why we take that work done by the work done by gas is negative. So in physics, our main purpose is work done by the machine, and in chemistry our purpose is what, how to increase the internal energy of the gas. So which factor increases the internal energy of the gas, we take that factor is positive, and which factor decreases the internal energy, we take that factor is negative. Here work done by the gas, as the gas expands, work done by the gas, as the gas expands, pressure decreases, temperature decreases, internal energy decreases, so work done by the gas is negative. In, if we compress, the pressure increases, that is temperature increases, that is internal energy decreases. That's why we take the work done on the system is positive. So confusion of sign convention in physics and chemistry, I hope cleared. So in we have to remember our main aim in chemistry is how to increase the internal energy of the gas, but in physics our main aim is how to get some work from the machine, This is thermodynamic process, thermodynamics process. Next topic is thermodynamics process. What is thermodynamic process? There are four process, main four process. First process is isothermal process. This is called also slow process. How this process is slow process, how this process called slow process, I will explain. And second, first I define the isothermal process, the process at which temperature, that is this temperature remain constant, remain constant. Here mean T is constant, temperature equal to constant. Now thermodynamic equation, what is the thermodynamic equation in isothermal process? Thermodynamic equation, first law, Q equal to del U plus W. Now as temperature constant, it internal energy constant, so change is 0. So we can write Q equal to W, only W, that is del U equal to 0. So isothermal process, del U equal to 0. Now temperature equal to constant in isothermal process. Now why it is called slow process? So to maintain the isothermal process, our process should be slow, our procedure should be slow. Suppose this is some gas is enclosed in a cylinder piston. Now to maintain the isothermal process, the container must be good conductor of heat. The container, here main condition is container must be good conductor of heat, good conductor of heat. So in the isothermal process, this is slow process, and our container must be good conductor of heat. Now why it is called slow process? To perform the isothermal process, compress the piston. We compress the piston. Now if the gas compresses, then pressure increases. Pressure increases means temperature increases. Temperature increases. Now our purpose is to maintain the temperature constant, to maintain the temperature constant throughout the process. So if we compress, then temperature increases, but if it may be isothermal when the temperature remain constant. So here heat must be rejected from the system when we compress. So to eject the gas, to eject the temperature, conductor should be good conductor of heat, and the process should be slow. The process should be slow because it takes some time to eject the heat. It takes some time to eject the heat. That's why it is called slow process. So to maintain the isothermal process, the process should be slow such that it takes enough time to eject the heat, because if not ejected, then the temperature increases, so that is not the isothermal. So to maintain the isothermal process, that heat should be rejected. As the heat takes some time, so it must be slow process. Adiabatic process. Now second process is adiabatic process, that is the process at which no exchange of heat between system and surroundings. No exchange of heat between system and surroundings. Suppose in ice cream box, some ice cream contains in the container in box. This box is thermocol, is insulated by thermocol. The substance is called thermocol. So as the whole box is insulated by thermocol, no heat enters from the system, from the outside to the inside, or here heat is not, no heat enters from this side to this side. That is no exchange of heat between system and surroundings. That is here Q equal to 0. So thermodynamic equation will be Q equal to del U plus W. Q equal to 0 here. So del U plus W equal to minus del U. So this is thermodynamic equation, and so main condition is Q equal to 0. Now it is called fast process. To maintain the adiabatic process, it is fast process or quick process. Quick process should be performed quickly. Quick process. Suppose in a thermal flask, water remain hot for 1 day, or less than 1 day, but for 10 days or 5 days the water does not remain hot anymore. So if the time is long, the process should not be adiabatic. So for adiabatic process should be, this is fast process or quick process. For quick process or fast process, it may be adiabatic. If it take enough time, then heat can be exchanged slightly. So if heat is exchanged, if heat enters into the system or heat rejected from the system, it cannot remain in adiabatic process. So that's why the adiabatic process is suitable for fast process or quick process. For long process, for if the process takes long time, then it cannot remain in adiabatic, because for long time some heat enters into the system or some heat rejected from the system. Okay. isobaric process, the process at which pressure remain constant, pressure remain constant. So thermodynamic equation is Q equal to del U plus work done. For work done we can write P into dV, isobaric process. Now next isocoric process, the process at which volume remain constant, that is V. When V is constant, then del V 0, then del V equal to 0, so work done del U plus work done, so Q equal to del U plus work done equal to 0 here. So isocoric process, when volume remain constant, Q equal to del U. Q equal to del U here, Q equal to del U plus PdV. First isocoric process, work done equal to 0 as volume V is constant, as the piston does not move, so work done equal to 0. And isobaric process, work done equal to constant pressure. Isobaric means pressure remain constant, P into del V, P constant pressure, P is constant pressure, Now third is isothermal process. What is isothermal process? What done in isothermal process? This is the derivation of what done in isothermal process. Let amount of gas expands from volume V1 to volume V2 at constant temperature T. Suppose constant temperature T is constant. Now gas equation is anytime PV equal to nRT. Gas equation equal to PV equal to nRT, where P and V varies. P and V varies, but T is constant. Suppose dW equal to work done to increase the volume of gas, from V to V plus dV. Work done to increase the volume of gas from V to V plus dV at pressure P. Suppose when small volume is increased, then pressure we take the pressure remain constant. So at constant at this pressure, volume of the gas increases from V to V plus dV. What is the work done? Work done will be constant pressure P into dV. dW equal to P into dV, because we take P is constant. If the volume increase is small, then we take this pressure is constant. If volume is expand more, then P does not remain constant anymore. The P does not remain constant anymore if the expansion of volume is enough. So we take pressure remain constant for small small increase of the volume P into dV. Now W got this total work done will be integration of dW, volume is V1 to V2. Now dW equal to P dV. Now the equation, gas equation is P equal to nRT. So P equal to nRT by V. From this P equal to, we put here P equal to nRT by V, P equal to nRT by V into dV, V1 to V2. So this will be nRT ln V, V1 to V2. So this will be nRT ln V2 . So as P1 V1 equal to P2 V2, so this we can take as log V2 by V1, log ln P1 by P2. This is called ln. Ln means when the base is E, we take this ln x. When base is E, we take this is ln x. Now what done by adiabatic process? So in adiabatic process, before finding the work done in adiabatic process, I will prove the equation P V2 bar gamma equal to constant. P V2 bar gamma equal to constant. I will prove what is the gamma. Gamma equal to Cp by Cv. I will prove what is Cp. Cp is specific heat at constant pressure and Cv is specific heat at constant volume. I will discuss. Gamma equal to ratio of two specific heat. So P V2 bar gamma equal to constant. I will prove that. First in adiabatic process, Q equal to 0. First in adiabatic process, Q equal to 0. Q equal to that is thermodynamic process is Q 0 equal to del U plus W. Now del U for 1 mole gas, heat supplied equal to, we take 1 mole gas, heat supplied equal to del U plus W. Del U equal to Cv dt equal to Cv dt equal to W. Work done. Now work done equal to, we know P into dV. So dt equal to P dV by Cv minus. Now we know PV. We know gas equation PV equal to RT. For 1 mole gas, we take 1 mole gas, PV equal to RT. If we differentiate both sides, we get R into dt. So this will, from this, dP into V by UV method, dP into V plus P into dV equal to R dt. So for dt equal to, so from this we get dt equal to V dP plus P dV by R 2, and this is 1. From 1 and 2, so from 1 and 2 we get minus P dV by Cv equal to VTP plus P dV by R. Now cross multiply, minus P R dV equal to V Cv dP plus P dV into Cv. Multiply here V Cv dP plus, shift at here, plus P dV Cv plus PR dV equal to 0. So take common dv vcv dp plus take common dv p cv plus r dv equal to 0. If we cv plus, now formula is cp minus cv equal to r, so cp equal to cv plus r. I will discuss how cp minus cp equal to r later. I will discuss cp minus cp equal to r in later. So cp plus r equal to cp. P into cp plus r equal to cp into dv equal to 0. So dividing both sides, by p into v, we get dp by p cv plus cp into dv by v equal to 0. cv into log p plus cp into log v equal to 0. Now divide cp by cv, gamma ln p plus cp by cv ln v equal to 0. ln p plus cp by cv gamma equal to 0. Equal to 0. So ln p v to the power gamma equal to 0. If we integrate this, then this remain constant. If we integrate both sides, this will be constant. Some constant, suppose k. So p into v to the power gamma equal to v to the power k, which is equal to constant, another constant c. So p into v to the power gamma equal to constant comes in this way. This is the derivation of p into v to the power gamma. If you integrate, this is not 0, this is k, another constant k. If you integrate both sides, this is k, this will come k. So p v to the power gamma equal to constant. What done by adiabatic process. So gas equation is, this is the gas equation, pv equal to nr p. Now dw equal to p into dv. Now so in adiabatic process, gas equation is p v to the power gamma equal to constant, p v to the power gamma equal to constant. Now what done, dw equal to, we know p into dv. So put here p c by v to the power gamma into dv. So total work done equal to integration of dw, which is v increases from v1 to v2. So dw equal to c dv by v to the power gamma. Okay, now c v to the power gamma minus gamma dv for volume v1, suppose pressure is p1, and for volume v2 pressure is p2. So this we can write this. Now multiply, see here 1 by 1 minus gamma is equal to c equal to this p2 v2 gamma v2 minus gamma plus 1 minus c p1 gamma minus gamma plus 1 by 1 minus gamma minus gamma. So P2 P2 gamma equal to, now P2 into this and this produce P2 minus this P1 V1 by 1 minus gamma. Now P2 equal to NR T2. So when pressure is P2, volume V2, then temperature is T2 minus NR T1 divided by 1 minus gamma. So what done in adiabatic process, formula becomes T2 minus T1 by 1 minus gamma. So this is the answer. What done in adiabatic process, this and this and these are the two formula of what done in adiabatic process.